Again, it's a rich thing.
What is going on, guys? Welcome back. In today's video we're going to talk about why Python is so slow, if it actually matters, and how to speed it up. So let us get right into it. Alright, so let us start with the very basics first, which are going to be central to what we're going to talk about in today's video. And the first point is defining what Python actually is. What is Python? And a lot of you guys, especially the beginners, are probably going to say, okay, Python is the programming language and what I'm running on my system. So when I type Python or when I open up the Python idle, that is Python. And that's not exactly true, because what Python is it's a language definition. A language definition, or you could say a specification. So this is just the structure of the language. What you're running on your system is not Python. What you're running on your system is CPython or Jython or IronPython or PyPy, an implementation of the Python language. Usually what you're running on your system is going to be CPython, not to be confused with Cython, which is a library that you can use in order to speed up your code. CPython is what you're probably running on your system. So if you just go to python.org/downloads, you download the version, you're probably running CPython, which is a Python implementation based on the C language. There are also other implementations like Jython, which is based on Java, IronPython, I'm not really sure what that is about, and PyPy, same thing here. But what's important is that there are different implementations and they also differ, because one of the 3 points that we're going to talk about today for why Python is so slow is going to be something that you will encounter in CPython, but not necessarily in Jython. So this is just something that you need to know. And the question we need to ask here today is, okay, if C is a super fast programming language and CPython is based on C, how can it be so slow? How can this happen? And Python is extremely slow if you compare it to languages like C++ or C# or C or Java. Python is extremely slow. And I really mean extremely slow. It's not just a little bit slow. It's really, really slow. And we're going to talk about today why that is. I'm going to give you 3 reasons. But one thing that I want to mention here right away is that Python is very slow when it comes to execution time, but it's very fast when it comes to development speed. So Python is super simple, and in a lot of application fields nowadays, it is more important to have a language that increases development speed, and it's not so much important to always get the highest performance. So of course, if you're in high frequency trading, or if you are programming airplanes or a Mars rover and so on, you want to have the most efficient code possible. Maybe you even want to write it in assembly. But in most areas, you're not going to be dependent on high performance, and your code is not going to be have to be optimized so that you get the last milliseconds of performance. Development speed is way more important. How fast can we deliver the product? So this is one thing that Python is definitely not slow at. So when we're talking about that Python is slow, we say Python's execution speed is very slow. All right, so let us talk about the first reason, which is that Python is an interpreted language and not a compiled language. And I would not say that this is the primary reason for why Python is so slow. This is definitely a factor. But I wouldn't say, okay, Python is slow mainly because it's an interpreted language and not a compiled language. It is a factor, but I think there are more important reasons as well. So the one does not mean that it's the most important reason. So when a language is interpreted and not compiled, this basically means that we have to translate the instructions to machine code during runtime. So let's say we have a basic program here. Those are just lines of code. And let's say this is C or C++, or a compiled language. What we do is we run it through a compiler. So this is a compiler. This is just a very superficial, high-level explanation here. But we have this code. It runs into a compiler and it produces machine code. So you could say zeros and ones here. So this is just a machine code that the computer understands. And once we have that machine code, that is already the program. So we just run this file, for example, on Windows, a .exe file. And that's it. We just execute it, and we don't need to do any translations. Of course, we do certain things during runtime, but we don't need to do anything fancy like, okay, this piece of code needs to be translated into machine code, because it already is machine code. It's already optimized for the computer. Whereas in Python, or in interpreted languages in general, what we have is an interpreter, and this interpreter doesn't interpreter. It doesn't translate the whole thing and then just execute it. It executes statement by statement. It translates statement by statement. So if we have something like print hello world, then what it's going to do is it's going to transform that statement into machine code and so on. And then the next statement is going to be transformed into machine code and so on, all over again. And in Python, you know, we have a lot of uncertainty, so you cannot just optimize it. Since it's interpreted, you cannot always optimize. You cannot say, okay, I'm going to compile the whole program, make it as optimal as possible, and then you just need to run it. No, we need to do it all the time. During runtime, we need to translate the code. And this is, of course, very, very slow, and it takes time because compile time is a thing that you have one time. So if you have a big program, you compile it. Maybe you compile it for a very long time, but once it's compiled, it's done. You don't need to do anything else. You just compile it and you have an executable, or maybe multiple executables, whatever. When you have an interpreted language, every time you run it, during the runtime, during the execution time, you need to translate the statements, which takes time. So this is definitely something that's slowing down Python. Also, what we don't have in Python, but what we have in other partly interpreted languages like Java, for example, is that we don't have a just-in-time compilation. So we don't have JIT. JIT is just-in-time compilation. Basically means that I have already a tutorial on this channel, I think, about Numba. You can take a look at it, where you can introduce JIT into Python. Basically means that you have interpreted code, but certain segments, for example, or maybe the whole thing, is interpreted just in time. It's compiled just in time. So this is the code. And then once you execute a certain piece of code, it is compiled during runtime, and the next time you execute it, it's going to execute the compiled code. So you don't need to interpret it again. You don't need to translate it again. But Python doesn't have a JIT by nature. So of course you can use Numba to speed up certain segments. But all in all, Python is completely interpreted. So this is one reason for why it is so slow. Reason number 2 is the Global Interpreter Lock, or short GIL or GIL, whatever you want to call it. And the basic problem here is that modern computers have multiple cores, and those cores can be utilized by using multiple threads. So we have quad-core CPUs, dual-core CPUs, maybe even more than that. And if you want to make use of that, you need to do that with multiprocessing or with multiple threads. So a process can spawn multiple threads. Threads share the same memory space, they have the same resources, and those threads can then communicate with each other easily, and they run concurrently, they run at the same time, and they process tasks at the same time. Now, what we also have with threads is we have so-called locks, and locks are not something bad. Locks are important for synchronization. So let me give you a very, very basic example. Let's say we have some basic resource here. This green dot is a resource, and then we have two threads. We have T1 and T2. Those are the threads. Now let's say T1 wants to change something in that resource. We want to increase, for example, if this is a number, we want to increase it. Now let's say T2 wants to do that at roughly the same time, and we also want to increase it, or we want to decrease it. We want to have two concurrent writing operations, or we're trying to do that at least. Now let's say we don't want this to happen. We don't want two threads or multiple threads to be able to manipulate the same resource at the same time. So they can still run concurrently, but if they are accessing the same resource, it needs to be locked. Or we want to have this in a synchronized way. So what we can do, of course, is T1 can say, okay, I'm locking this here. I require a lock, then I'm increasing it, then I'm unlocking it again, and then T2 is going to lock it and change it and unlock it again. So this is a very not sophisticated, superficial definition and explanation of locks, but it's not too important here. We use locks in order to synchronize threads. Now in Python, or in CPython at least, what we have, I have written Python here, by the way, CPython. In CPython, we have something called reference counting. So for each variable, we store how many references we have to that variable. So we have some variable, let me just pick another color here. We have some variable A here, and let's say we have some references to that variable. Now, once those references are gone and reach number 0, this is going to be freed. Again, a very superficial explanation, but we don't want to go into too much depth here. we have this reference counting here, and in order for that reference counting to also work when we have multiple threads in CPython, we have something called the global interpreter lock. So basically, this means that the interpreter can only process one instruction at a time, basically killing multi-threading. So since we have that global interpreter lock, the interpreter is never able to process more than one instruction at a time, which basically means you can start 1,000 threads, you're still going to only have one instruction at a time because you have this global interpreter lock. And this affects CPU-bound tasks or CPU-bound threads. So if we have something where we have a lot of computation concurrently, this is going to massively affect performance. In fact, it's going to not be multi-threading at all. It is not affecting I/O-bound tasks. So for example, if we have input that we're waiting for, or if we have, in general, idle time, this is not a problem. So we can still asynchronously do certain things. We can simulate concurrency, but we don't have actual concurrent programming in Python because we have this global interpreter lock, at least in CPython, which brings me to the last point. In Jython, for example, and I'm not sure if this is also the case in other implementations of Python, but in Jython, we don't have the global interpreter lock because Jython profits from the JVM environment, Java Virtual Machine. So here we don't have a global interpreter lock. This is just something that you might want to look into if you're interested in that. And also what we can do is we can do a multi-processing, because multi-processing is not the same process with the global interpreter lock, but multi-processing spawns multiple processes, and all of these processes have a global interpreter lock themselves. Those are individual interpreters. So multi-processing definitely works. So last but not least, let us get to the final reason, which is Python is dynamically typed. And in my opinion, this is the main reason for why Python is so slow. In Python, we don't need to specify statically any data types. So when we have Python code, what we do is we say A equals 10, B equals true, or C equals hello. And then later on, we can even say, okay, A, it was an integer up here. It's now going to be a list of strings and booleans and all sorts of things. We can mix things up and so on. And of course, this can be very convenient for programmers. It's very flexible. We can always change things. We can still do type checking manually, and we can also do type hinting. Type hinting is not influencing the code. It's only influencing the readability. So it's not influencing the actual program in the end, but you can say, okay, we're expecting an integer here, we're returning an integer here, we're expecting a string here, and so on. So it's just for readability and documentation purposes. So you have the predictability on a code level, on a readability level if you want to, but there's no compiler or interpreter that knows, okay, this is going to be an integer for sure. The types are always dynamically determined during runtime. So every time we have a variable A, we need to say, okay, what is A? Is it an integer? Okay, A is an integer, so we're going to treat it as an integer. But later on in the code, A might be a string, or it might be a class. Yeah, it can actually also be a class. It can be an object. It can even be a function. It can be everything in Python. So we're super flexible here. And every time we read or we write into a variable, we need to do a type check every time. And this is all happening during runtime. We don't know what it's going to be. It can change the type. Even if we figure out, okay, A is a list of strings, it can change. It can change, and in a couple of lines of code, A is going to be an integer. So we have no predictability, which makes code optimization extremely hard, if not almost impossible. And this is radically slowing down Python because we don't have we cannot optimize the code. We have no compiler or no interpreter that can just say, okay, I know this is going to be that type, this is going to be that type, this is going to be predictable here, so we can reduce it down to that. No, we don't know what's going to happen. We can even determine types during runtime. So I can even change, I can say, okay, A equals something, and I can change the type during runtime. And because of that, code optimization is extremely hard, and we're not going to have fast code execution because statically typed languages are just faster. This is just a truism. And flexibility in Python comes at cost of the speed. Everything's dynamic, everything is easy and simple, and we can do all sorts of things without problems, but this comes at the cost of speed. at the cost of execution speed. Finally, let us talk about the conclusion. Is this really a problem or doesn't it really matter? And as I already said, development speed nowadays trumps execution speed in most fields. It's more important because we want to have developers being able to write code quickly, to change code quickly. We want to have a fast development speed, and it doesn't really matter for most things if the execution speed is the best one we can have. Now, of course, if you're into 3D game development, if you are into low-level hardware programming, if you are programming with limited resources, if you're programming in a field where performance is very important, you're not going to use Python in general. You're going to use C, C++, maybe assembly. And for this, I want to bring up the finance example because I have read a little bit about how finance programming is done. And basically what I read in different articles, and I also watched a couple of videos, is that in finance, what you do is you have Python for prototyping models. So, okay, you want to know this is a new algorithm I came up with. This is a new machine learning model that I came up with for stock trading, for example, technical analysis stuff, for example. And what you do then is you implement all this in Python in order to prototype it. So you just develop the whole thing, the whole algorithm, the whole model in Python, and then you try to back test it on data. You see, okay, how well would it have performed in the past? How well does it perform now? But you don't put it into production because it's super slow. And in finance, everything is about milliseconds. You want to be the fastest. You want to be the first one. So it's good enough to do it in Python because in Python you can change stuff, you can experiment around easily. But once you know, okay, this model is very good, this algorithm is very good, I want to use it for my stock trading, you're not going to run it on Python unless, of course, you know you're doing something in the long term. But if it's high frequency trading where everything is about milliseconds, you're going to take this model that you have developed in Python and you're going to implement it in C, C++, and sometimes even assembly as optimized as possible. So this is an analogy or an example here on how things are done if performance is needed. Python is used for its development speed, and if really high performance is needed, you're going to use C, C++, or assembly in the end. So let us talk about a couple of solutions that we have here, at least ways to speed up Python code. And I think for those two, I even have a video on my channel. So Numba just-in-time compilation, you can introduce JIT for certain segments, for certain functions in Python to massively speed them up because you're using just-in-time compilation. This mainly works for mathematical computations, and for NumPy, it doesn't work so well with pandas or scikit-learn, for example. And we also have Cython, which introduces static typing. So with Cython, we can use C types, static typing. There you go. So with Cython, we can introduce C types into Python. And if that's not enough, we can even program whole C extensions. So certain pieces of code written in C executed by Python to massively speed up performance. So maybe I'm going to do a video on that in the future as well. And what I have also read in the internet, but I have no guarantee here that this is actually true, there is actually some work being done on improving Python continuously. There are always new Python versions, and maybe there are speculations that maybe sooner or later the global interpreter lock will be removed with something more intelligent. Maybe we're going to find a better way of maybe even compiling stuff, certain pieces of code. Maybe we will have static types in some way by nature, even though Python remains dynamically typed. But for now, we don't know what's going to happen. So if there are some major updates, I'm going to make a video on them, which is why we want to be subscribed on this channel. So if you want to know new Python things, so whenever a new Python version is released, I usually make a video what's new in Python 3.9, what's new in Python 3.10, 3.11, and so on. So if you want to stay updated, you want to make sure that you're subscribed and hit the notification bell, right? So if there is some update on Python, it is getting faster and faster because of improvements, I'm going to make a video on that. Alright, so that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and